Alright, after that video on capacitors from UC Davis, you might be rightfully wondering, well, what exactly is a capacitor? A capacitor is a thing that stores charge, and in that way it's kind of like a battery, but a battery works by chemical reactions. Capacitors work by the placement of electrons on a conductor, or basically anything that can hold excess electrons. Current can't flow through a capacitor, so if you've got a simple circuit, let's say, with a capacitor, and the symbol for capacitor are two parallel lines that are the same length, and so it is similar to a picture to the battery symbol. So the battery is one long line, one short line, or a series of long and short lines. When you hook up a circuit, there's a gap here in the capacitor with some distance d, and current will not flow through there. So even though current can flow through the rest of the circuit while there's a capacitor, so current can go there, current can go there, charges will not actually move in between the two plates. So if I zoom in over here, you might imagine like, oh, well, a charge can move from here to here, but it won't. Charges don't move from one side of a capacitor to another, at least if the capacitor is working properly. What does happen, though, and the UC Davis video talked a little about that, is electrons will leave one side of the battery. So let's just imagine one electron that leaves the side of the battery and comes over to the capacitor. And so now the electron is stuck here on the capacitor because the battery is creating a potential difference, or as I have started using the analogy, a height that the electron needs to fall. But the capacitor kind of like stops it. It's like a guy sticking out his hand and stopping a kid going down a slide. So you've stopped the person on the slide. The electron is stuck right there, even though they want to fall the rest of the way. The guy from UC Davis said, and in the same way, the battery might pull electrons off the plate, and that's exactly what happens. Electrons get pulled off that top plate. The analogy, though, that I keep in my head, and that I like a little better, I think it makes a little more sense. Once an electron comes right here, it will repel an electron that was on the plate. So an electron gets stuck on the bottom plate, and then that electron will repel an electron on the top plate. And so an electron on the top plate will want to get away, and that electron on the top plate, the farthest it can get away, is the battery. And then later on, another electron gets stuck on the bottom plate and repels another electron from the top plate. And that's how you charge up the capacitor. You create an imbalance of charge between the two plates, even though if you think about it, the net charge on the two plates overall would stay zero, because every time you add an electron on the bottom, you kick one loose from the top plate. And that's the analogy I keep in my head. Every time we get an electron on the bottom plate, it kicks an electron on the top plate off via its electric field. So the electric field from the electron that's now added to the bottom would force an electron up here to move away. Finally, capacitors do produce uniform electric fields. So if we had a capacitor set up, this one that I've drawn here, an electric field would form from the positive charges on the top plate to the negative charges. And because we've got them packed together, their electric fields bend each other in two straight lines. So they basically unbend each other and produce uniform electric fields. Now you might remember from the last unit that since when we have a uniform electric field, we can use this equation, E equals V over D. So if we know the electric field, we can find the voltage using the distance between the two plates, D. If we know the voltage, we can multiply and find the electric field. So capacitors do produce uniform electric fields, to which we can apply the equation E equals VD. Sorry, V over D. E equals V over D. Finally, capacitance depends only on the plate geometry. So the things that determine capacitance, if you look at the equation up here, the area of the two plates, and the technical definition is what's called overlapping area. So it's just the area of each plate, not the total area. So if we know the area of this plate, that would be the same as the area of the bottom plate, and we'd stick it into the top. Now the first time I saw this equation, I had the question, so I'm going to go ahead and answer it for you. What if we had two plates of different area? What if we had big area and small area? The A that you use in the equation is in the area of the smaller plate. It's the overlapping area, so just the area that they both share. All of that to say, it's not the total area, because that can be a little confusing. You might start to think, wait, do I need to add the area of the two plates? No, it's just the area of one of them. Any capacitor you're going to deal with, both in my class and even if you got a job dealing with capacitors, should have areas the same on the top and bottom plate. So you just pick one, because they're going to be the same, and use the area. The capacitance also depends on the distance between the plates. So you might notice as you increase the distance, capacitance decreases. Capacitance is basically the amount of charge per voltage you can put on that plate. As you increase the area, you can put more charge per voltage onto that plate. Now the charge Q refers to the stored charge on the positive plate only, and that's because if we were to refer to the charge on the whole thing, charge on the whole thing is 0, because every time you've gained an electron on the bottom, you've knocked one loose on the top. And so we just said, well, the charge will be the same on both plates, just one positive, one negative, so we're going to opt to only talk about the positive plate. Finally, capacitance has the unit farads, named for Michael Faraday, who did some famous experiments with electricity. Capacitance has the units farads, F. And just to review kind of the essential equation for capacitance, capacitance equals epsilon naught, which is a constant, the area of the plates, and the distance between them. That is also equal to the charge per voltage you can have on the plate. Now that does mean as you change the voltage of the battery that you use to charge the capacitor, the amount of charge you could store on the plate would change. And so we can hook up different batteries to different capacitors and get a different total charge on that capacitor. But for any given capacitor, the charge per volume would be the same. And that charge per volume depends only on the area of the two plates and the distance between them. Most of the stuff you'll have to do with this equation is manipulating it. If one thing doubles, what happens to the other, and so forth. Those are the kind of questions you get generally asked on the AP Physics B exam. Alright, that's it. Have a good night, and see you tomorrow.